Okay, finally, we'll talk about some of the future demands for pulsar timing systems and the technology that's been developed for processing the data that comes through. With a single receiver in a single dish, then we've got a very small spot on the sky that we're actually looking at. If we put multiple receivers up there, we get better sky coverage. We can look at more sources at once. But of course, that generates more data, and we need more data processing capacity to handle that. Now, the low-cost design we've got for Hebe, the whole system cost about £10,000, can be simply replicated for each of the receivers. There's a back end for each of the receivers. So if we have 4, 8, 12, once we start to get bigger numbers of receivers on the dish, then other designs may come in where there's far more GPUs in a server than just 2. Phased array feeds is a different type of multiple receiver, where the signals are all combined together to give what's called a beam on the sky, a focused beam of information from a particular area. One of the tricks with this is there is another processing step between the receiver and the digitizer and the pulsar timing system, because we've used some fairly complex mathematics to actually do real-time beamforming. So we get all the information from all of the different antennas that we've got looking at the sky, and we want to focus on a particular area. We use a beamformer to take that information and extract it from the massive data that we're receiving. And then we pass that information, that particular beam of information, through to the pulsar timing system. So that starts to depend on the processing capability of another back-end system. And you still may need lots of different pulsar timing systems to sit behind that to actually process the data from each of your individual beams. We talked about data rates from 512 megahertz bandwidth receivers. Now, the ones at Katunsi at the moment is 150 megahertz at 5 gigahertz and 300 megahertz at 6.7 gigahertz. Ultra-wideband receivers can be 800-900 megahertz at different frequencies. And of course, with that amount of extra data, if you go from 512, say, to 800, because of losing information along the way, you've doubled the bandwidth. So you need at least double the processing capability and post-processing to bring the information together from the whole of the bandwidth and the whole of the different timing systems that you use. There are new phenomena that have been detected since the pulsar timing was developed, but can be seen with pulsar timing systems. For example, fast radio bursts. These are nominally extragalactic in origin. We can see that by looking at the dispersion measure of the signal. They're very fast, typically a couple of milliseconds in duration, very bright, so a single pulse is detected. Some repeat, some don't. And you're never quite sure where they're going to come from or where they are, whether they're going to repeat or not. But a pulsar timing system, because it looks for the very narrow pulse from a pulsar, has the resolution to detect FRBs. And what we'd like to be able to do is process the same data in real time, looking for fast radio bursts as when we're doing pulsar timing. More processing demands. And one of the things we've considered, for example, is a third GPU in Hebe dedicated just for searching for fast radio bursts. Okay, so that's the end of the talk on back-end systems. But before we close, I just want to show one more slide, just because I quite like this one. It gives you an idea of the timescales that we're looking at And we're going from events, models, predictions of 1 times 10 to the minus 18th of a second, up to events currently 10 to the 9 seconds, 32 years and more. And we're looking at variability in pulsar sources and behaviors across that kind of period, across that magnitude of difference. That's 27 orders of magnitude. And that's data we can process and deliver using a pulsar timing system. Okay, thanks very much. If you have any more questions, let's take those live.